In the throttling process of the CET subject, we are discussing Joule-Thomson coefficient. So recently, we already discussed the Joule-Thomson coefficient, which is given by this is mu is equal to del T by del P divided by H, where the during the expansion the value of delta P pressure change is negative. Okay, સો એની અંદર આપણે જુલ્સ થોમ્સન કોફિશિયન્ટને પોઝિટિવ લેવા માટે શું કરીએ છીએ, ડેલ્ટા ટી નેગેટિવ છે બરાબર, તો એને શું કરીએ છીએ ત્યાં આપણે કુલિંગ ડેલ્ટા ટી શું થાય છે નેગેટિવ, એટલો એનો મતલબ થાય છે થ્રોટલિંગ વખતે શું થાય છે કે થ્રોટલિંગ પ્રોસેસ દરમિયાન કુલિંગ થાય છે. ના ધ next part or a next topic is it is compressors. So compressors are exactly which having a various part to complete the process. So we exactly we completed, okay, in the IC engine, EC engine. Okay, so compression process, which types of compressions. Okay, so let's see. So compressors may be reciprocating types of turbo type. Reciprocating હોય છે બરાબર, we know that. Reciprocating types compressor are used for developing high pressure ratio, whereas turbo type compressor are preferred for a high volumetric flow rate. Turbo type compressors are preferred for a high volumetric rate. The general energy equation are applicable for the both side. So adiabatic compressions, for the adiabatic compression, gas under negligible changes in the kinetic energy and potential energy, so it will be written as a Ws equal to minus delta S. So the minimum shaft works are required for compressing a gas adiabatically from a given initial state to given discharge pressure is the isentropic work, which is given as a Ws isentropic, that is delta H of S, where delta Hs is the enthalpy change accompanying by isentropic process, isentropic compression. So the ratio of this isentropic work to actual work required for the compression is the compressor efficiency. Okay, so compression efficiency ને કઈ રીતે ડિફાઇન કરી શકીએ? It is the ratio of it is the ratio of isentropic work to actual work required to compression. It is called the compression efficiency. So let's do the integration of the shaft work equations. So equation 5.7 can be used to evaluate a shaft work required for the developing of given pressure ratio in the reversible operation. So it is Ws is equal to integration of minus P1 to P2 VdP. And for the ideal gas undergoing isentropic compressions using the relation PV raised to gamma is constant, we already discussing and derived it. So now from the 5.70 crane we've written as a PV is equal to PV raised to gamma is constant. So P1 V1 is also raised to gamma is constant. Now so V is equal to now compare these two. So PV raised to gamma is equal to P1 V1 raised to gamma. So V is equal to P1 by P, V1 raised to 1 by gamma. Now this equation is in the value of V put into the this 5.70 and the result is given here. Okay, equation number 5.46. So the work compression for ideal gas may be written in terms of initial and final temperature. So that is delta H Cp delta T. Okay. Now the work this equation 5.446 is the adiabatic compressions equations. Okay. Then next isothermal isothermal compression. So for the reversible isothermal compression 5.10, it becomes Q is equal to Q minus delta H. So the Q is equal to T of delta S. Put this here. Now simplify that. Delta H tends to 0 in becomes of enthalpy changes. Enthalpy of ideal gas depends only on temperature. Enthalpy છે શાના પર H is equal to U plus PV. Okay, but the enthalpy change of the gas is depend only on the temperature. So delta H is equal to 0. So delta S is equal to R ln P2 upon P2. Just pushed into the equation 5.18. So therefore it will be Ws RT ln P1 by P2 is equal to the RT ln V2 by V1. P1 is equal to P1 V1 is equal to P2 V2, and we simplified that, so it is like that. So also here replacing V is equal to RT by P. PV is equal to RT, so V is equal to RT by P simply. And this equation is shaft work isothermal compression for ideal gas. The next is multi-stage compressions. The reversible isothermal and adiabatic path of compressions of an ideal gas from initial pressure P1 to final pressure P2. Shown in figure 5.4. Adiabatic and isothermal compression on PV diagram. So P1, P2 and the various parts is given, that is A, B, C, D and E. So A to B, this one is a reversible adiabatic compression. A to B and E to C is the reversible isothermal. Okay. And the PV diagram, exactly what happened in the PV diagram of three-stage adiabatic compression with interstage cooling. So P1 to P2, and here exactly isothermal expansion and isothermal compression having, and then 3-stage 1, 2 and 3-stage compression with intercooling. So equation is over here. Ws is gamma minus 1. This one is a similar equation for the that is gamma upon gamma minus 1 RT1 1 minus P dash upon P1. So the remaining equation is from for 5.15, and it is for the multi-stage compressions from the figure 5.4 with n stages. Number of stages are n. Then the equation 5.50 can be written as a, if the compression ratio in all other three stages are equal and denoted by R, then the total work required may be written as a Ws is equal to n gamma upon gamma minus 1 RT1 1 minus R raised to gamma minus 1 upon gamma. In writing equation number 5.51, it is assumed that after each stage the temperature of the gas is brought down to initial value, and it can be slowed down for the minimum total work in multi-stage compression. So the pressure ratio in all the stages are equal to given by R P2 by P1 raised to n, where the P2 by P1 is the pressure ratio, we know that. The next point is that coefficient of performance. Okay, this one is we discussed already in the heat engine and heat pump. So let's recall it. Refer figure 5.7. Symmetric representation of refrigeration cycle. This is refrigeration cycle. So low temperature reservoir to heat is given to the it is converted to the high temperature reservoir. Exactly work on this system. Okay. So the let Q2 be the heat that is absorbed by a low temperature T2. Heat Q2, let Q2 heat શું થાય છે એબ્ઝોર્બ થાય છે at low temperature T2 પર, બરાબર. અને heat and Q1 be the heat reject. Q1 છે એ શું થાય, heat reject કરે છે at higher temperature T1 પર, બરાબર. So the by first law of thermodynamics, we know that first law of thermodynamics, Q is equal to so it is U is equal to Q minus W. Okay, now W is Q1 minus Q2. Work is the difference between the Q1 minus Q2. So the first law is that delta U is equal to Q plus W. Okay, now the efficiency or coefficient of performance, efficiency अथवा तो coefficient of performance for a refrigerator is defined as the quantity of heat absorbed at a low temperature per unit of work. Quantity of heat absorbed, that is Q2 divided by refrigerator, is the quantity of heat absorbed at the low temperature per unit work, that is W. So it is Q2 by W, and W is given by Q1 minus Q2. Okay, now the next one is that the refrigeration cycles, all these types of refrigeration cycles. So let's see refrigerator capacity. Refrigerator capacity determines the rate of circulations of the refrigerant, which is turns decide the design and the size of the various units such as a condenser, compressor, evaporator and the expansion devices. The refrigeration capacity is determined the rate of circulation of refrigerant, which is design and size of the various units such as a condenser, compressor, evaporator and the expansion devices. And then the capacity is sometimes measured in tons of refrigeration. 1 ton is defined as the heat absorptions at the rate of 12,000 BTU per hour. It is absorptions. 1 ton is it is absorbed 1 ton per 1 ton. That means 1 ton is defined as the heat absorbed at a 12,000 BTU per hour. 1 BTU is the amount of heat is required to raise the temperature of 1 pound. It in other way, 0.4536 kg of wet water by 1 degree Fahrenheit or 1 by 1.8 Kelvin. So the 1 BTU is 1.055 kilojoule. This rate corresponds to the rate of heat removal that is required to freeze 1 ton of water in a day, originally at 273 Kelvin. And the 1 ton of refrigeration equivalent to refrigeration rate of 12,660 kilojoule per hour in the SI unit. So the refrigeration cycle, in which another base type or the maximum use of the important play role in the CT, which is Carnot cycle. Okay, so let basic overview of the Carnot cycle. So exactly, Carnot cycle can be used as a model of ideal refrigeration cycle because of all the refrigerations operating between the same two thermal reservoir. This one is a low reservoir to high reservoir. Okay, cyclones as Carnot cycles can be used in the model of ideal refrigeration cycle. Refrigerator operating between the same two thermal reservoirs. The maximum COP is attained by the one of the based on the Carnot cycle, and this is depicted in figure 5.8 8a. એટલે જે coefficient of performance from the two reservoir thermal reservoirs, lower and higher. The COP is attained by one based on Carnot cycle, and the Carnot refrigeration cycle is shown in figure. So the detailed instruction or detailed learning about this Carnot cycle we will discuss in the next lecture. All these types of refrigeration cycles, which having the limitations, advantages, and which where it is used, what is the advantages. Okay, so all these cycles we discuss in the next lectures.